We showed previously that transmission lines are completely characterized by two fundamental properties: the complex propagation constant and the characteristic impedance. So together, those two terms tell us almost everything we need to know about the transmission line. And so complex propagation constant gamma and the characteristic impedance Z0 are what are typically used to characterize a transmission line. And if you recall from our earlier discussions, both of those can be calculated from the distributed parameters and angular frequency. So if I know R prime, L prime, G prime, C prime, and omega, I can calculate both of these from two pretty simple equations. The complex propagation constant gamma is just the product of R prime plus J omega L prime times G prime plus J omega C prime. Take the square root of that, and the characteristic impedance looks pretty similar, except that instead of a product, it's a division. So it's R prime plus J omega L prime divided by G prime plus J omega C prime. And that's a C up here as well. I know it looks like an L, but that's a C. So just given these parameters, we can completely characterize a transmission line, complex propagation constant, and characteristic impedance. A lot of times we're going to make an assumption about the transmission line, and we already alluded to this. We call it a lossless T-line. And in a lossless T-line, the series resistance is much smaller than the series reactance, and the shunt conductance is much smaller than the product of the angular frequency and capacitance. In both these cases, we'll just take the logical extension that since R prime and G prime are much lower than their associated parameters, then we can make the approximation that R prime is equal to 0 and G prime is equal to 0. And again, we called this, previously we called it the lossless T-line assumption. And it gives us some interesting results if we plug it into our equations for complex attenuation constant and characteristic impedance. So R prime goes to 0, G prime goes to 0 in both these equations. So we'll just do that math real fast. Gamma is going to be equal to 0 plus J omega L prime times 0 plus J omega C prime, which is going to be equal to J squared omega squared L prime C prime, which is just equal to J omega times the square root of L prime C prime. So in general, not in the lossless case, but in general, gamma, when we take the square root of the number, we're left with a real portion and a imaginary portion. And as we showed previously, this real portion corresponds to the attenuation constant in Nepers per meter, and the imaginary portion corresponds to the wave number in radians per meter. We see that from the lossless approximation, the complex propagation constant only has an imaginary component. Therefore, in the lossless case, alpha equals 0, and beta is equal to omega times the square root of L prime C prime. So that's a simplification for the lossless T-line. Similarly, if we looked at the characteristic impedance, it's going to be the square root of 0 plus j omega L prime over 0 plus j omega C prime, which is just equal to L prime, the square root of L prime over C prime. And so in this case, there's no j omega term. So normally, in the general case, Z0 is equal to some sort of resistance plus j times some sort of reactance, and that's normal. In the general case, the lossy case. In the specific case of the lossless T-line, we see that R0 has got to be equal to 0 ohms, and that Z0, or that, sorry, that's not true. R0 is equal to the square root of L prime over C prime, and X0 is equal to 0 ohms. Right? We have only a real component. There's no J here. Despite the fact that there's an L prime and a C prime under this square root, the end result is that the characteristic impedance is purely real. So that's kind of a surprising but important result. And since we often use the lossless T-line approximation, I've summarized these here. There's just one change. There's a little typo right here. You need to make that 0 plus j beta. So gamma is equal to j omega square root of L prime C prime, which is equal to 0 plus j beta, and then Z is equal to the square root of L prime over C prime. So very important results, important enough that I've summarized them here. An additional conclusion you can draw from that is that we can calculate propagation velocity from 1 over the square root of L prime C prime. And then if we're using coax, I'm not going to show the math, but if we were to apply the distributed parameter models, the math for calculating the distributed parameter models, you would eventually arrive at the result that Z0 is equal to 60 over the square root of the relative electric permittivity times the natural log of the inner radius of the outer conductor divided by the radius of the inner conductor there. So let's just get some practice with actually doing some calculations. We want to calculate all the associated parameters of a transmission line given the distributed parameters and a frequency. So if we were to do this math, we need basically two functions. We need R prime plus j omega L prime, and we need G prime plus j omega C prime. A lot of times I'll calculate these as a total because we use them so frequently. So this is just 0.25 ohms per meter plus j times omega, which is just 2 pi f, so 2 pi times 1 e to the 6. And then we need to multiply that by distributed inductance, which is 200 nanohenries, or 200 e to the minus 9 henries. And since that's a reactance, it's also measured in ohms per meter. And so that's going to give us a complex number, which is 1.2812 at an angle of 1.3744 radians, which if we were to write that in real plus imaginary format is 0.25 plus j 1.2566 ohms per meter. Similarly, let's calculate G prime plus j omega C prime. That is equal to 1 micromole, or 1 microsiemen. So that's 1 times 10 to the minus 6 plus j 2 pi times 1 e to the 6 times the capacitance, which is 100 pico. Pico is 10 to the minus 12. And that's going to give us 1 times 10 to the minus 6 plus j 6.2832 times 10 to the minus 4 mhos per meter for that. And if we were to write that in rectangular form, or sorry, polar form, it's going to be 6.2832 times 10 to the minus 4th at an angle of 1.5692 radians. So gamma is just the square root of this times that. So that's going to be the square root of 1.2812 at an angle of 1.3744. And we're going to go ahead and multiply that by 6.2832 times 10 to the minus 4 at an angle of 1.5692. And that gives us a complex propagation constant of 2.804 times 10 to the minus 3 plus j 2.8234 times 10 to the minus 2. This here is alpha in Nepers per meter, and this here is beta in radians per meter. We were then asked to calculate the propagation velocity. Propagation velocity can be calculated from a variety of ways. We just calculated beta, so I'll use omega over beta. That's going to be 2 pi times 10 to the 6 divided by 2.8234 times 10 to the minus 2 gives me 2.225 e to the 8th meters per second. I'd get the same answer if I had used propagation velocity is equal to, 1 over the square root of L prime C prime, whatever form you wanted. And then finally we were asked to calculate characteristic impedance, and that's going to be the square root of this quantity divided by this quantity. So that's 1.2812 at an angle of 1.3744 divided by 6.2832 e to the minus 4 at an angle of 1.5692, all in radians, and that gives us a Z0 equal to 45.16 at an angle of minus 0.0974 ohms, which if we write that as in its real and imaginary components, it's going to be 44.95 minus J 4.392 ohms. And so we see that this lossy transmission line has a complex characteristic impedance.